Welcome to Calculus 1. In this lecture, I'll be introducing the limit of a function. Let's begin by introducing the limit geometrically. Consider this function here, which is 10 plus 5x when x is not equal to 0, and undefined when x is equal to 0. There's a discontinuity at x is equal to 0. That is, there's a hole in the function. So what value does f of x approach as x approaches 0? Well, we can make a table where we have x in one column and f of x in the other. When x is equal to negative 1, f of x is 5. When x is equal to negative 0.5, f of x is 7.5. We can continue making values of x closer and closer to 0. And we notice that when x is equal to negative 0.0001, f of x is 9.9995. We can approach x is equal to 0 from the right side, so when we start with x is equal to 1, f of x is 15. When x is equal to 0.5, f of x is 12.5. We can continue making x closer and closer to 0, so when x is equal to 0.0001, f of x is equal to 10.0005. So intuitively, as x approaches 0, f of x approaches 10. So we call the number that f of x approaches the limit of f of x as x approaches 10. And recall that when we make x infinitesimally close to some number c, for example, we're making x closer and closer to the number 0, but not exactly 0, we use something called the limit notation. So we say the limit of f of x as x approaches c is equal to L, where f of x is some function. In our example, we say the limit of 10x plus 5x squared divided by x as x approaches 0 is equal to 10. Let me now introduce a bad definition of limit. Given f is defined on some open interval that contains c, except possibly at c itself, we write the limit of f of x as x approaches c is equal to L if we can make the values of f of x arbitrarily close to L, that is, as close to L as we like, by taking x to be sufficiently close to c, but not equal to c. I invite you to pause the video to read this over so you can understand what it means before moving forward. So why exactly is this a bad definition? Well, first, we say if we can make the values of f of x arbitrarily close to L, but what exactly do we mean by arbitrarily close? Second, we say by taking x to be sufficiently close to c, but how close is sufficiently close? So far, we only have an intuitive understanding of the limit, but that is not good enough. The limit underpins everything in calculus, from differentiation all the way to integration. In order to put calculus on a firm footing, we need a logically rigorous definition of the limit, and that will be the topic of our next lecture. For now, let's talk about different types of limits. We will begin with the side limits. Consider the function shown here. We see that it's discontinuous at x is equal to 0.1. We can also see that the value that f of x approaches when x approaches 0.1 from the left side is equal to 2.9. So we say the limit of f of x as x approaches 0.1 from the left is equal to 2.9. We can also see that as x approaches 0.1 from the right, f of x approaches negative 0.2. So we say the limit of f of x as x approaches 0.1 from the right is equal to negative 0.2. In general, we have the following notation and say that the limit of f of x as x approaches c from the left is equal to L if we can make the values of f of x arbitrarily close to L by taking x to be sufficiently close to c and x is less than c. As an exercise, I invite you to write a non-rigorous definition of the limit of f of x as x approaches c from the right. We also can say the following. The limit of f of x as x approaches c is equal to L if and only if the limit of f of x as x approaches c from the left is equal to L, and the limit of f of x as x approaches c from the right is also equal to L. So the left-hand and right-hand limits must be the same number for the overall limit to equal L. Now let's talk about infinite limits. We can see that as x approaches 2 from both sides, the function goes towards infinity. That is, the function grows arbitrarily large as x approaches 2. We can also say that there's a vertical asymptote at x is equal to 2. So here's a non-rigorous definition of infinite limits. Let f be a function defined on both sides of c, except possibly at c itself. Then the limit of f of x as x approaches c is equal to infinity means that the values of f of x can be made arbitrarily large, that is, as large as we please, by taking x sufficiently close to c, but not equal to c. We call x is equal to c a vertical asymptote. As an exercise, I invite you to write a non-rigorous definition of the limit as f of x tends towards negative infinity. We can also have limits where x approaches infinity. So here, we can see that as x approaches infinity, the function approaches 2. So we say the limit of f of x as x approaches infinity is equal to 2. In general, we have this non-rigorous definition of limits at infinity. Let f be a function defined on some open interval p to infinity, where p is a real number. Then the limit of f of x as x approaches infinity is equal to L means that the values of f of x can be made sufficiently close to L by making x arbitrarily large. Here, we call the line y is equal to L a horizontal asymptote. As an exercise, I invite you to write a non-rigorous definition of the limit of f of x as x approaches negative infinity. Now I want to present the final example. Consider the function of f of x here. As x approaches 0, what does f of x approach? Well, in fact, as x approaches 0, the function oscillates infinitely between 0 and 1, so f of x does not approach a single finite number. Here, we say that the limit does not exist. In fact, we have already seen several examples where the limit does not exist. For example, when the left-hand limit is not equal to the right-hand limit, we say that the overall limit does not exist. When the function goes up towards infinity, we also say that the limit does not exist. We only use the notation equals infinity to denote that the function is not bounded from above. However, the overall limit does not exist because infinity is not a number. And finally, if the function goes towards negative infinity, the limit also does not exist for the same reason. I leave you with an exercise. Consider the function f of x, whose equation is in the top left corner. Based on the provided graph, try to evaluate the limit of f of x as x approaches 0.